Hello everyone. I call myself Mr. U.S. Patil, working as assistant professor at Sharad Institute of Technology, College of Engineering, Edra, Ichalkarji, which is at Kolhapur district, Maharashtra. Today, we're going to see the boundary conditions in FEA, finite element analysis or finite element method. So, let's get started with the boundary condition. Boundary condition for the model is the setting of a known value for a displacement or a associated load. For a particular node, you can set either the load or the displacement, either load or displacement, but not the both. It's a very important point. At the boundary condition, the loads and constraints that represents the effect of the surrounding environment on the model. That is everything else that you have not modeled. If you see, the main type of loading available in FEA include force, pressure and temperature. These can be applied to points, surfaces, edges, nodes, and the elements are remotely offset from future. The way that the model is constrained can significantly affect the result and the required special consideration as well. When we say the boundary conditions are constrained, necessary for the solution of a value problem, a boundary value problem is a differential equation, or you can say system of differential equation to be solved in a domain on whose boundary a set of condition is known. It is opposed to the initial value problem, in which only conditions on one extreme of the intervals are known. When it is opposed to the initial values problem, in which only conditions on extreme of the intervals are known, but boundary values problems are extremely important as they model as vast amount of phenomena and applications. For solid mechanics to heat transfer, from fluid mechanics to acoustic diffusion, they arise neutrally in every problem based on the differential equation to be solved in space, which initiates value problems usually referred to problems to be solved in time. The boundary values problems have been extensively studied by Jockey Charles Francois Sturm, the duration of 1803 to 1855, and Joseph Liouville, the duration of 1809 to 1882, who studied the eigenvalues of linear differential equation of the second order, and they studied the condition which guarantee the existence and uniqueness of the solution of the differential problem and how it is affected by boundary conditions. The Sturm-Liouville theory is extremely important for the computational problem because it enables the understands if the problem is well posed and how it is possible to obtain the solution. When we say the finite element method is a numerical technique to solve physical problems to predict their responses. Now we in order to solve the problem numerically, we need to have mathematical model of the problem. This is done by obtaining the governing equations, right? If you see the type of boundary conditions, and both ordinary and partial differential equation need boundary conditions to be solved, and the different type of boundary conditions can be imposed on the boundary of the domain. This is a resolution of domain and boundary, and the choice of the boundary condition is fundamental of the resolution of the computational problem. If it's very important that if you have bad imposition of boundary condition may lead to the disadvantage of the solution or to the convergence to wrong solutions. If you took a wrong boundary conditions or you have given a wrong boundary conditions, so it might have a wrong solution. When the governing equation describes in the form of equation the behavior of the system, it will be functions of the field variable and the displacement. That is, field variable is nothing but you can say the displacement or temperature, etc., and or its derivatives. If you see cross-sectional properties, you can say area parameter, area moment of inertia, etc. The material property 1, that is Young's modulus, conduction coefficient, convection coefficients, etc. But the governing equation alone is not sufficient to describe the behavior of the system. So we need to provide additional boundary conditions for boundary value problems and initial conditions, that is for initial value problems. The boundary conditions are of two major kinds. Actually, I have here we have three kinds, but in that there are two major kinds. First one is essential or geometric or Dirichlet boundary condition. These are the boundary conditions that describes the condition of the primary variable or field variable, that is temperature, displacement, etc. And the next or second one is neutral force, natural or force or Newman boundary condition. Second one, Newman boundary conditions. These are the boundary conditions that describe the condition of the secondary variables, and the secondary variables are quantities that are functions of derivatives of the primary variable. So here in the Dirichlet boundary condition is a type of boundary condition named after Paulette Peter Gaston Lejeune Dirichlet. It's in 1805 to 1859. This condition specifies the value that the unknown functions need to take on along the boundary of the domain, boundary condition of that domain. For example, the Laplace equation, the boundary value problems with the Dirichlet boundary condition is written as delta phi of x, that is equal to that proportional to the omega. This you can say equation 1, and phi of x, that is function of x, that is again x is of proportional dou omega, where phi is the unknown function and x is the independent variable. This x is independent variable, that is spatial coordinates, and omega is the function domain, and dou omega is the boundary of the domain, and f is the given scalar function defined on dou omega. If you see in this framework, the numerical simulations, it is usually imposed directly in the algebraic system to be solved. Let's consider the following algebraic system derived from a numerical algorithm, that is k11, k12, dot dot dot, like that, and k1 m minus 1, k1 in m, k21, k22 dash 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 dash, similarly k23, k24, etc., and k2 and km minus 1 and k2 m. Similarly, km minus 1 and 1, km minus 1 2, km minus 1 3, etc., dash dash dash, and km minus 1 m minus 1, and here km minus 1 into m. This is what one matrix, and of x vectors x1 x2 dash x3 x4 dash dash dash, xn minus 1, and last is xn, and here equal to a1 a2 a3 a4 a5 am minus 1 am, where kij are the element of the algebraic operation or operator, you can say operator. For example, the stiffness matrix xir, this is x1 x2 xr, are the unknowns, that is the degree of freedom of the problem. We need to give a degree of freedom that accordingly, and ai are the known terms. The simplest way to impose a Dirichlet boundary conditions on the nth degree of freedom is to modify the system as follows. Degree of freedom of nth term. So k1 11 up to k1 m, and this nth term is in between here somewhere in the nth term minus 1. So here 1 0 0 again. So here km up to kmm. Yes, so this is x1 x2 x in between xn here, again x1 minus 1 x1 up to xn. So a1 here force, that is f, and am, that is where f is the value that the nth term and the degree of the freedom must be taking. If you see next, that Newman boundary condition, in the Newman boundary conditions is a type of boundary condition named after Charles Newman in 1832 to 1925. When imposed on the ordinary, that is ODE, or partial differential equation PDE, is specifies the value that derivative of a solution is going to take on the boundary of the domain. And if you give an example for the Laplace equation, the boundary values problems with the numerical or Newman boundary condition is written as phi of x equal to 0, where x is I proportional to omega, and where dou phi into of x divided by dou n, that is equal to f of x, where x is proportional of dou omega, where n is the unit normal to the boundary surface. This boundary surface, if omega is r raised to 3. In case of ODE, that is omega is of r raised to 1, if you say the derivative normal to the boundary coincides with the global derivative of phi dash. In the rare cases in which temporal dependency is solved through a finite element approach, that is instead of more usual finite differences. This type of boundary condition is the most common. The numerical boundary condition is also called natural because it is naturally appears in the development of the weak formulation in any finite element approach. And if you see, this is one third one that is not much used or common kind of, and this one is, this is not kind means it's not considered a major what you say kind of here boundary conditions again, but there is a Robin boundary condition. In the Robin boundary conditions is a type of boundary conditions named after Victor Constable Robin, that is Robin 1855 to 1897. It consists of a linear combination of value of the field and its derivative on the boundary. For example, Laplace equation boundary values problem with the Robin boundary condition is known as delta phi of x equal to 0, where x is of omega and a phi into x plus b and dou phi into x divided by dou n equal to f of x, where a and b are the real parameters. So this condition is also called impedance condition. In a mixed boundary conditions, it is consist of applying different type of boundary condition in a different parts of the domain. It is important to notice that the boundary condition must be applied on the whole boundary. The free boundary is anyway subjected to homogeneous, where we see that a Newman boundary condition, and the mixed boundary condition offers from the Robin condition because the latter consists of a different type of boundary condition applied to the same region of the boundary, while mixed condition implies a different types of boundary conditions applied to the different parts of the boundaries. If you see the Cauchy boundary conditions, this is another one. The Cauchy boundary condition is a condition on the both the unknown field and its derivatives. If differs from the Robin condition because the Cauchy condition implies the imposition of two constraints. One is direct boundary condition and plus a Newman boundary condition, while the Robin conditions implies only one constraint on the linear combination of the unknown functions and its derivatives. That's why that is not major kind of Robin boundary conditions. These two are the direct boundary condition and Newman boundary conditions are a major kind of. If you see the applications of these boundary conditions in structural and mechanics, if you see the directional boundary conditions, here solid mechanics is usually modeled through a displacement based model. Uh, Thus, direct boundary conditions usually consist of imposing the displacement of the structure is given a point, and the structural mechanics is often based on the formulation which includes relative rotations here, and whose numerical resolutions requires non-linear shape functions in the finite element approximations. If you, for instance, the frame structures are based on the beam theory and the related finite elements has 6 degree of freedom, that is 3 displacement plus 3 rotations in 3D space, and for 2D problems each node of the boundary has 3 degree of freedom on which Dirichlet boundary conditions can be applied. And if you say the two displacement, that is ux and ux and uy, and one rotation, that we can say omega. If you see in a Newman boundary condition in a structural solid mechanics, in solid mechanics the special derivatives of displacement are related to the strain tensor, and in elasticity the strain is proportional to the stress. Hence, the Newman boundary conditions refer to both imposed strain and stresses, since the stress is also linked to a external force through the Cauchy stress principle. And the Neumann condition is also used to apply external loads. As stated in the section dedicated that the Neumann boundary conditions, the homogeneous condition is naturally satisfied. So free boundaries may not be modeled explicitly here in Neumann boundary conditions. If you see a Robin boundary condition, as we say, this is not as a major kind of, it is used to model the mechanical impedance of structure. That is how it resists to motion when subjected to a harmonic load. Then if you see in a fluid mechanics, the boundary conditions in fluid mechanics by Dirichlet boundary conditions. In computational fluid mechanics, the classical Dirichlet boundary condition consists of the value of velocity and or pressure to be taken by a certain set of nodes. It is common to refer to some sets of boundary conditions according to the some terminology. That is, if you see a slip boundary condition, the terminology, if you say that slip boundary condition where the velocity normal to the boundary is set to 0, while the velocity parallel to the boundary is let free. And second is no slip boundary condition, in that both the velocity normal to the boundary and the velocity parallel to the boundary are set equal to 0. And if you see, at least one homogeneous boundary conditions on the pressure, that is, you can say, has to be imposed as a reference for open domains, and for instant in the highest boundary of the air domain. And if you see a Neumann boundary condition, the constraints on the derivative of velocity or pressure fields are mainly used in two cases. The first case is the application of the symmetry plane, and the second application is the modeling of the wall friction. And if you see the Robin boundary conditions, it is used to describe the semi-reflective walls which partially absorbed waves. It is not a very common application, and it can be used only for pressure based models. It is mostly used for acoustic applications. If you see a thermodynamics in the direct boundary conditions, in thermodynamics, Dirichlet boundary conditions consist of surface, that is 3D problems, held at fixed temperatures. And if you see Neumann boundary conditions, in thermodynamics, this Neumann boundary conditions represents the heat flux across the boundaries. And the perfect insulator reflects a homogeneous condition which is naturally satisfied. And while all warmed and cooled boundaries are required to explicitly assign the boundary conditions. This is normally the case with electronic components or external cooling spray or channel, like that. So if you if you see the electromagnetism, in the field of electromagnetism, the boundary conditions uh, this is Dirichlet boundary conditions in electromagnetism. The Maxwell equations are commonly solved through in potential formulation actually. So in Dirichlet boundary conditions usually imposed on the boundary sections of the conductive domain. In the case of wires, the values of one section are normally set to 0, while a fixed value of the electric potential is fixed on the second section, and the conditions usually constrained the magnetic field to be tangent to the external boundary, that is to have all the magnetic lines inside the computational domain. If you see the normal boundary condition, if you see the normal boundary conditions in a electromagnetic model under a certain hypothesis, this imposes the homogeneous and normal boundary conditions, right? So this is what boundary conditions which have been gone through, and this is what a brief explanations about the boundary conditions and the kinds of the major kinds of the boundary conditions. So we'll see in the next video for the further points. Thank you one and all.